So in this topic, we'll start the discussion on linear fracture mechanics. Now, when we say linear elastic fracture mechanics, we are basically talking about the following. So first of all, we are assuming if I can draw for you the stress strain curve, right? We are saying that it's linear, okay? You're going to stay in the linear realm, and you're going to be below your proportional constant, okay? So this is a proportional limit. Proportional limit, and any stress below this will be completely valid. Okay, so do understand, and it's elastic because we have not exceeded your sigma yield. Your sigma yield is somewhere here. Okay, it's tensile yield. This is yield strength, and as I told you previously, sometimes this is also called the tensile strength. Okay, so given the fact that we are actually doing this, this is the region we're working with. Let's start with some definitions. So if you want, you can pause your video and you can take this notes on these definitions. But basically, what we are talking about, every structure is under this basic assumption. Every structure has some sort of crack, okay, has some sort of flaw. It can be microscopically big, it can be as small as microscopic, and it can be due to many reasons, okay? And the whole idea to study fracture mechanics is the following. So the field of fracture mechanics is responsible to study cracks, how the cracks propagate. Okay, so it is nothing else than a study of cracks or crack propagation. Also, it comes. It is. We use this. This is a methodology that's used to aid in selecting materials. And designing components to minimize the possibility of failure. And the main assumption, every structure has some small flaw. Okay? And fracture mechanics is based on three main modes. We call them typically mode 1, mode 2, mode 3. You can think about if you think about a plate, right? and this plate has an edge crack, and you're pulling this, immediately you can see how this crack is going to tend to open up, right? And it's going to look like more mold 1. You can have the case of a joint, right, where you got a bolt here, and you got a screw, and then you're pulling this on this side, you're pulling this the other side. So this is called mode 2 type of crack. This is really rarely seen, but you do have these cases in which especially twisting. So there was a way that I was actually twisting a structure, then this mode failure will show up. In reality, all 3 modes act at the same time. You rarely have a pure mode 1, pure mode 2, or pure mode 3. Okay, what is important to memorize here, and this is where you may want to stop the video and take some notes. This is in your book, by the way. This is called opening, and this is a tension problem. This is sliding. This is in plane problem. This is mode 3, out of plane problem. One example of this could be the aircraft panel, in which I have a crack here, and now I got some pressure loads at the bottom, right? I got some pressure loads here, and I have another pressure and something that's holding this here, so it will not actually deflect in this direction. So I have pressure loads going this direction, pressure loads going this direction. So this is actually crack is going to make me want to go one direction, another direction, creating mode 3 that's tearing. Okay? So with that said, let's see what really happens. So in the previously, when we did this discussion, we talked about, let's say I have this small hole that is pure tension. So think about this as an infinite plate. Because it's infinite plate, then the stresses are basically become uniform in this location. So now this is nothing else than starting. This is the plot starting here. Okay, what would happen? Sorry, starting right here. Okay, so this plot right here will look something like this. Okay, if I was going to plot this. So if I was going to just use your stress concentration factors, right, you can show the stress concentration factor at this particular point will actually look something like this. 1 plus 2 times A over B times sigma, where A is the half of this ellipse and B is the width of the half of the width of the ellipse. This is what we actually learned in our previous topic. These are stress concentration factors, right? However, look what happens if now, think about this, if I take that small crack and I make this crack this distance, keep my A equal, but make this small. So as this becomes smaller and smaller and smaller, this flattens out, creating a full crack. So what happens? Let's say if A over B, let's say is equal to 1, it's a circle, and you can actually show that this is 3. If it's actually 2 times now, A over B is 2 because this is 1/2 of that distance, become 5, and 3 then becomes 7. So as A over B tends to infinite, as this term actually goes to complete infinite, and so when this goes to infinite, what you can show is this is all your KT right here. Your KT goes to infinite. So that doesn't make any sense to me. I'm saying my stress rises actually go to infinite, which is actually true because I'm working with discontinuity, right? I really have a crack. I have a structure that actually is cracked. This is a singularity. Because there's a singularity, it's going to have infinite stresses. So in this particular case, as you can see, stresses are no longer useful. So in a crack, we cannot use stress analysis only. Okay? because I still may be able to use stress and see if this is going to hold for stresses, because I can take this area, right, minus this area that's left and see if that's going to hold. But I still need to do fracture mechanics analysis. Okay, so what do we really do? What are we going to do then? So what are we going to do? Instead of using stresses, we have something that we call fracture toughness. Okay. And what is fracture toughness? Fracture toughness is a new quantity that we use by letter K. And this K is not the stress intensity factor. This factor actually tells me what is the limit value of K necessary for my crack to start to propagate. So this tells me the limiting value at which my crack, the crack will propagate. Okay? So that limiting value, we call it letter C. And we'll talk about that in a moment. Just give me a sec. Now, the what we call the fracture toughness of the material is the capacity, the K is the capacity of the material to resist crack growth. Okay, and then what we do here is at the bottom we can have subscripts. So for instance, if I have K1, this is fracture toughness for mode 1. Okay, so fracture toughness for mode 1. If I say this is K2, this is fracture toughness for mode 2. And same for K3, right? If I have K3, this is fracture toughness for mode 3. Okay? Now, before we continue our discussion, there are a couple of things that play a big role into crack propagation. And one of the things that play a big role is the plastic zone. This plastic zone actually is the one that's responsible for this crack to propagate or not to propagate. If I have plasticity, it gives me a break for my material to actually go through the cushion. Think about this like a damper, right? So it can go there. It's not going to propagate too fast, but once it's gone from the plastic zone, it's just gone, okay? Then it just propagated. That's what happens with the material. So the plastic zone plays a key role in my structure, okay? Plastic zone, localized plastic zone plays an important role. Okay, so let's see. So what I told you is this is the capacity of my material. This is how much my limiting value is. So this value, this limiting, has to come from testing. Okay, and the testing is actually there's a table in your textbook. Let me find the table number for you. So this is the table 5.1 of your textbook. And this is mode 1 fracture toughness. Typically, what we do is mode 1 fracture toughness is equal to from this value. But then if you wanted mode 2 sometimes is simply 0.866 times KIC, or we can have other means of relating mode 2 and mode 3 to K of mode 1. But this is beyond the scope of this course, and we would just limit ourselves to mode 1, okay? So these are the various fracture toughnesses. This is the yield strength of the material. In my notes, you will see that I give you a more comprehensive and complete list, and actually includes the unit in KSI and inches. So consider using this, my notes as well as a reference. But these are all giving you fracture toughness KIC. Okay, this is what you are really having. Okay, so now there are a couple of things that you have to keep in mind when you're doing this type of analysis. When I'm doing this analysis, what I am really trying to do is I'm trying to find, I am trying to see if my limiting factor, right, that's my critical factor, divided by how much I really have available, what I need is actually bigger than 0. That becomes my factor of safety, right? And this has to be, again, as we know, this is bigger than 1, this is safe. If this is equal to 1, this is onset of fracture. And if it's less than 1, it has failed. Okay, so what is this quantity looks like? This quantity is equal to K times beta times pi A. In general sense, this is what it is. So I will get back to this in 1 second, but I want to still talk about this particular parameter right here because it's very important. This parameter is going to bring some interesting results for us that are very useful. Okay, so to do that, let's again, you're going to have two different type of analysis if you're working a thick plate or a thin plate. A thin plate is plane stress, a thick plate is plane strain, and in this particular case, what is important is this parameter right here. Your Q is equal to 2.5. So basically, what you're saying is your T here, your T is bigger than 2.5 times KI SY squared. Here, to be thin, consider thin, has to be less than 2.5 KI divided by SY squared. So now pay attention very closely what happens. This is the value that you get from testing, okay? This value is what you get from testing mode 1, K1, okay? And this is for plane strain. This is for this case. This is where my test data actually comes from. But I may have the case where my thickness is smaller than this, and you can see I got a bigger cushion now, right? Because if I have a stress value, let's say hypothetically, I have a stress value that's over here, right? And that was my stress value, but then I had my thickness here. Well, if you just use the value that's given right out of the table, gives you the idea, wait, this is how much I have available, but I need more. It looks like I failed. Well, you maybe not failed because you realize that you actually plane stress if it's less than it's less than your critical thickness, right? Then if it's less than your critical thickness, then it is plane stress strain dominated. In that case, your equation will be different. Okay, so your T of S is actually going to equal to 2.5 K1C YT squared. So in such a case, if we are working in plane stress, the equations that are valid will be the following. Okay, in that case, you're going to use a correction factor, Kc, is going to equal to KIC okay, square root of 1 plus 1.4 t squared KIC divided by y yield strength squared. Okay, so this is the relationship. Basically, this is for anything in this region, okay, from this region and some t sub 0. So if you're in this region right here, you should use this equation as your limiting value instead of using your KIC that you get from your tables. And this is going to bring you some relief, okay? But we will do more examples and you probably will understand this better as we move on, okay? So let me summarize a few things here before we move on. So your limit value, okay? You're going to check your t. Okay, if your t, your t, and that your t transition is given by KIC sigma yields squared. If your t is bigger or equal, if it's bigger than TS, then just use the value KIC from table. Now, if your t is less or equal than ts, then use the equation, your kc will equal to the value from the table. But otherwise, use kc equal to kic square root of 1 plus 1.4 t squared KIC divided by sigma yield to the fourth, okay? A nice equation that's very convenient to use, and that's the equation form that we'll be using in this course. It just simplifies our analysis. You can approximate this as following. TS divided by T and squared, okay? Squared, not to the fourth. Here's the fourth, here's the squared. Okay, so this equation becomes very handy and it greatly simplifies our analysis. Okay, so with this said, let's see what we do now with our analysis. So I told you that in our equations we had the following, right? I had K, what 1, let's say, was equal to beta sigma. I forgot the sigma in my earlier equation, so please add that sigma times A. Okay, I think here here at the top, when I define that somewhere here, yes, right here, it should be beta times sigma. There's a sigma missing there. Okay, so that sigma is very, very important. So this is going to depend on the figure. This is the crack length. And I'm going to put length in quotes, and I will explain that in a minute with the tables. Okay, crack length. This is the modification factor. I will explain that in the next chart as well. This is your nominal stress. Nominal stress with no crack. Okay, just think about I don't have any crack present. As for an example, I got a plate, right? I have a crack, center crack, and I'm pulling. Okay, and at this particular location right here, I'm going to evaluate the plate. I want to know the stress is where, exactly where the crack is, right there, without no crack. and that is this stress that I'm pulling right here, okay? Assume there's actually no discontinuity there. That's the value that goes there. Now, there's some nice charts in your book, okay, that tell you exactly what they look like. If you have a crack on that, you have to look at the figure very carefully and know what your A and B are, right? So this is 2 times B, 2 times A. So in your equation, when you say you're using your beta and you're using pi A, this pi, know that it's half of the crack length here in this particular case. This beta factor is a ratio, okay? It's the distance from here to here is A. So this is small. If you go to your textbook, figure 525, A over D, okay? Depending on the ratio that you have, you come over here and then you can find this value, and that will be the value of beta that you use, a correction factor, okay? And if you have a different case, maybe a case that edge cracked, in this particular case, know that your Ki is actually equal to beta sigma pi A again, but in this particular figure, your A is actually equal to full crack length. It's not half the crack length. It's going to depend on the case by case. So in this case, you also do your A over B, and that will give you a value, right? And that value will give you another value here. That's the value of beta that actually goes inside there, okay? So if there's a beta rectangular, if a rectangular cross section, and it's actually it actually has a crack there, and it's having a bending type of behavior, you still use the same equation. Okay, the equation does not change. The values of A changes. Now A is only half of that crack. You may have a case in which now you have something like this, where you have a hole, but you have a crack. So in this particular case, you're using still is half the crack length from here all the way here. Not only this, the whole thing. Okay, it's very, very important you know this. And then you have these curves, and you still use the same equation. This equation is not going to change. If you have a tube, and I want you to think I got a crack right there, right? So this crack right here, you can see that there is a crack here and a crack there, right? In that particular case, this is what this equation looks like, and so on and so forth, right? And then you have a pressurized vessel type of problem, and this is what your cracks look like. Okay, so to better understand this, so now there is a criteria in which we can determine if I have a crack, okay, if there is a crack in the structure, is it going to fail due to yield, or is it going to fail due to fracture, okay, crack propagation. So we have a nice criteria that helps us to do that. We got something we call the critical, we got something we call the transition length. Let me write it down here. Transition length. Okay, and that transition length is equal to 1 over pi KIC divided by sigma yield squared. Okay, this is the transition crack length right here. Okay, if your crack length is less than the transition crack length, then it's going to fail because of yielding. And you can see this, right? Look at this. Think about, I got this structure, this is my yield line. I cannot have any stress above this line. If my crack is over here, now I go up, I go up, I go up, I go up, and I go up. Oops, I cannot reach this curve at all. I cannot get there. Why? Because it's going to fail because of yielding first. This is my limiting value. I cannot go beyond this. So therefore, it actually fails because of this. If it's actually bigger or equal, okay, and 0, obviously, and is bigger or equal than this, then in that particular case, you can see that if my crack is here, my yield line is up here, but it hits this curve first. So my limiting value of my stress is way below sigma yield. So therefore, the limiting value will be the fracture limiting value and not my yield limiting value. So it's very nice. The couple of things that you have to keep in mind. First, you make sure that your T, if your T is bigger or equal than TS, right? This is for your critical value. So this is a done deal. Otherwise, you make the correction. If it's less than TS, then you make a correction to KC. Then you have to come and check your crack. The crack of the structure. Is the crack bounded between 0 and the transition length, or is it bigger than transition length? If it's smaller than this, then check for yield. There's no need to check for crack for fracture mechanics at all. It's the crack is not going to propagate. So when you actually design structures, you know what this transition length is going to look like, and you measure it. You got people measuring all the time and seeing if it's going to be safe or it's not going to be safe. Okay. So this diagram is very important to understand, and this is actually the backbone of everything we do. Okay, so this concludes our theoretical discussion on linear elastic fracture mechanics.